Find the current flowing through 10 ohm resistance in the following circuit using Norton's theorem. We know that for this we have to make a Norton's equivalent circuit which consists of a single current source, that is called Norton's current, with in parallel with a single resistance called Norton's resistance Rn, which is parallel to the load resistance given, and the load resistance given is 10 ohms. So our RL is 10 ohms, and we have to find the current I, or we can say IL, flowing through RL. Okay, this is also IL, but we have to find using Norton's theorem. So we have to make Norton's equivalent circuit. Now we have RL, but we have to find IN and RN. So let us first solve RN, that is Norton's equivalent resistance or Norton's resistance. So the first step in solving for Norton's resistance is that we have to remove the load resistance. So let's remove the load resistance. Now the second step is all the independent voltage sources should be short circuited, that is, this is voltage source, it should be short circuited, and all the current sources must be open circuited. So let's apply to our circuit. Now you can see that I have applied it. So there is no use of this hanging wires. So let us remove it because no current flows there. Now we have to solve for Rn across these terminals. We can call this as AB. So we have to find the equivalent resistance across these terminals, and we can see that only one resistance is there, that is 20 ohms. So our Rn is equal to 20 ohms. Directly we can write because only one resistance is there, that too across AB. Now as we have got Rn is equal to 20 ohms, now let us solve for the current In. And before solving In, please note that the same procedure for Rn and Thevenin's resistance also, same procedure is there for finding RTH also. Okay, now coming to In, the first step is to short our load. So 10 ohms is our load, so we have to short it like this. Now we have to calculate the current flowing here, which will be our In. Now for solving In, first let us take KCL at this node. Let this node be N. So if we apply KCL, it is Kirchhoff current law. That is the sum of currents going into the load is equal to sum of currents going out of the node. So let this be current I1. Let this be I2, that is 30 amperes, and let this be IN. I am not writing I3 because already IN is there. So currents going into the node is only I1 is equal to currents going out of the node, it is I2 plus IN. Right, is capital also. Now we can also substitute the value of 30 amperes here. It is 30 amperes plus IN. I1 is equal to 30 amperes plus IN. Let this be equation number 1. Now as this is a special case in which the current source is in between the two branches, we can apply a super mesh. Super mesh is like this. That is, we will take the KVL of this by rejecting or neglecting the current source coming in between of the two branches. This is known as super mesh analysis. But remember, we have to take the individual loops only. This is I1 and this loop is IN is flowing like this. Now we have to take out the KVL, apply KVL in this loop. So we have to consider this only as one single loop as shown by the blue arrow. Okay. But please note that we have to consider two different currents only, I1 and IN. But we have to write in a single equation, single KVL equation. So let us start applying KVL, that is 60 volts, 60 minus 20 I1 because I1 is flowing here, and coming to here IN, no, we cannot see any resistances or individual voltage sources. So this completes our loop. So equal to 0. That is KVL state that the sum of the voltages inside a closed loop is equal to 0. So from here we get I1 is equal to 3 amperes. Now from equation 1 we already had I1 is equal to 30 plus IN. Now let us substitute 3 amperes in I1, that is 3 is equal to 30 plus IN. Therefore IN is equal to 30 minus 3, that is 27 amperes. This is our Norton's current IN. Now we have got Rn is equal to 20 ohms and IN is equal to 27 amperes. Now let us assign this value in Norton's equivalent circuit. Now let us solve for the current IL, that is our load current flowing through RL, that is 10 ohms given in the question. Now let us solve it by current division rule. Now as per current division rule, for example, source current is there. Let it be represented by IS. And the current is divided between two resistance, example R1 and R2. Let this be current I1 and let this be current I2. So now we have to find any one of the current. Example, we have to find the current I2. So as per current division rule, how to find I2? I2 will be equal to the source current multiplied by the equivalent resistance divided by in which branch I2 is flowing, R2. So we have to write R2 here. Like this we have to find using current division rule. Where R equivalent is how they are connected, R1 and R2 parallelly they are connected. So equivalent parallel resistance is R1 into R2 divided by R1 plus R2. So let's apply this current division rule in this circuit to find the current IL. So just now we have seen current division rule. So IL will be equal to source current. What is the source current here? This is the source current. IN is the source current. So IN multiplied by R equivalent. R equivalent will be RN or RL parallel to RL divided by in which branch the IL is flowing, which we have to find out, RL branch. So write the current RL. So first let us do RN parallel RL, that is 20 ohms parallel to 10 ohms. The equivalent will be 20 into 10 divided by 20 plus 10, which will be equal to 20 by 3 ohms. And we know that RL is 10 ohms. So IL is equal to 27 amperes into 20 by 3 divided by RL. RL is 10. So we will get 18 amperes. So IL is equal to 18 amperes, which is the current flowing through the load resistance of 10 ohms. So 18 amperes is our answer. Thank you.